Hello and welcome to Easy Projects. So I'm trying to make a karaoke machine. It might sound very fancy, but it's actually just a computer with a program on it called Ultrastar Deluxe. It's open source and free for everyone to download. You don't get any songs with it though, so you need to own the songs and you can then download the lyric files. It works really nicely, but I ran into a problem with my audio interface. I had two dynamic microphones already, but the problem is the preamp in the audio interface doesn't amplify it enough. When I crank it up to full, it only shows about 2 bars on the audio meter. It sorta kinda works, but if people are not singing very loud, it starts to clip out on the low end. Buying a microphone preamplifier is actually not that expensive, but since this is really just for fun and it doesn't need the greatest audio quality, I thought about why not try to make a very simple one by myself. The only requirements really being that it is better than just digitally amplifying the signal. That's always an option in the PC. You can just add gain, but that also increases the noise, like the white noise, at the same amount, so you just get like in the background, and then the program can't read the signal anyway, so you might as well just leave it low. So that's really all the requirements. It should be no audible distortion, obviously, and then no background hiss. Or maybe we will get a bit, but just as low as possible. And also, talking about microphones, I bought a lavalier microphone to try out with my camera here. It's pretty inexpensive, but so far it seems like it's working a treat. Obviously this could be done with your typical computer headset microphone, just plug directly into the PC. But it's just more fun with a real microphone. So that's why I want to make this amplifier. Looking at the parts I had available here at home, I found an LM324 op amp. It seems like it's suitable for the job. It can take a voltage from 3 to 32 volts. I plan to operate it from a single 9-volt battery, so that should be fine. It has 4 channels. Actually, that leaves us with one spare that we can use as a power indicator if we want, to check if the battery voltage is still fine. But again, the LED uses most of the power then, so maybe you don't want to do that. So these are dynamic microphones, and I'm really only interested in making it work for these, because I think we can take a few shortcuts then. The output of one of these microphones oscillates around 0 volts. It's basically just an inverse speaker, and as the sound hits it, it starts vibrating and it creates an electrical signal. If we power the op amp from 0 and 9 volts, we can really only get the signal to swing around either of them, and then we would cut half the signal. So we had to do something to shift the 0 point to the middle of the op amp's operating range, so say 4.5 volts, so that when the signal swings, it maybe swings down to 4.4 up to 4.6. There's a few different ways we can do that, and here I will be using, perhaps someone will call it a naughty trick, because it really only is suitable for the dynamic microphone. We can make a voltage divider, say by 2 10 kilo ohm resistors. That will give us 4.5 volts at this point, and the op amp can buffer that signal, so we can source or drain some current through the output and still maintain 4.5 volts. There's no naughty thing about this, but when we feed this voltage directly through the microphone, it has a very high impedance, around 500 to 600 kilo ohm, and then we feed it back to our audio amplifier. That makes sure that the input of the audio amplifier also is at 4.5 volts when there's no signal. Else we will have to make some kind of a bias circuit that would interfere with the impedance of the microphone and perhaps eat away some of the signal. There's ways to do that, obviously, if you want to use more components, but I think just taking this voltage and feeding it to the microphone is the simplest one. And it will come apparent later why this will only work if the microphone doesn't give any DC offset to the signal. To make this voltage more stable and to avoid the channel popping when you turn it on, you can put a capacitor here and to ground, and also a small capacitance here to ground. You should always be careful about adding capacitance to the output of op-amps because it can be unstable. Usually a small amount doesn't do much. If you do get a problem, you can put a resistor in between here, and that will greatly increase the amount of capacitance that the output can handle. Again, this feedback has to go here now, obviously. When we take the feedback here, the resistor doesn't affect the output voltage, but it does allow the op-amp to accept more capacitance. To make the audio amplifier, I just use a op-amp channel and make it into a non-inverting amplifier. If we feed the output back to the inverting input with through a resistor, and then we take another resistor, normally to ground, but this is our common point, so in this case it's 4.5 volts. As the current runs from the output to the common point, the two resistors makes a voltage divider. The higher the division ratio, the less voltage the op-amp will see at the inverting input. The op-amp always amplifies until the two inputs are the same, so having a lower feedback gives you more gain. In other words, when you increase the division ratio, you get a higher gain. And you can get that either by increasing the resistor that goes from the output to the inverting input, or decreasing the resistance from the inverting input to the common point. It has the same effect. Or we can write a formula like this. Remember that the amplifier amplifies the difference between the two inputs. So if there's just a small variation here, the output will have a very large offset. That is why it's important to have exactly 4.5 volts at the input here and also at the input here. You can see if we do nothing to the input, we will have just 4.5 volts here. The amplifier will amplify it until there's 4.5 volts here, but since this node is also 4.5 volts, that means this should be 4.5 volts as well. So everything is 4.5 volts. Any offset between these are then multiplied by our gain here. So if we set a gain of, say, 10, and we have 100 millivolt difference between these two signals, we'll have 1 volt difference on the output. So as you see, just a few hundred millivolts difference between these inputs will throw the output entirely out of the range of the amplifier. To make sure that it works with all microphones, we should really AC couple the input, and then we should make our bias ourselves. But because the microphone is so high impedance, the current that it delivers is very low, and if we use normal value resistors to make our bias, the bias resistors will just eat up all the current. We can do that by using higher value resistors. So you must excuse the fancy screen recorder here, but some of the important parameters for an op-amp are the input offset voltage. I mentioned before that if there's an offset between the two inputs, then the output will be that offset times the gain. Even if the inputs are completely the same, so say exactly 4.5 volts each, then the internal accuracy of the op-amp will add typically 2 millivolts to that. So if we have a gain of 10, we will get a 20 millivolt difference on the output. So it could be 4.52 volts. In this case, it's not a problem, but for very high precision circuits, you could run into problems. You can get it much higher than 2 millivolts, and you can get it much lower than 2 millivolts. When we come to using high value resistors for the biasing, you can see this op-amp doesn't have a very high bias current. So we could probably get away with it. But the thing is, if you put a very high value resistor, you can have up to 100 nanoamps running through that resistor and either into or out from the input of the op-amp. That current creates a voltage drop across the resistor, and you get more offset voltage. So that can also ruin your day. In this case, I don't think it would be a problem, and maybe we could have done it that way. But it just adds more components, and honestly, I didn't really try it out. But feel free to experiment with that, obviously. So we connect this through our microphone to the input, and we also connect these 4.5 volts together. We duplicate this circuit, so we make 2 channels, and then we have 1 op-amp left. We can use that as a comparator and check the battery voltage. So if the battery voltage gets too low, the amplifier won't work anymore, obviously, and we can make an LED to indicate that, so that it lights up green when it's working. If you just use it for karaoke, it's probably not a problem if it suddenly runs out, but if you use it for something important, it's nice to be able to see the battery level. In my case, I might just leave it out because it uses power, and I have to change the battery sooner. On the other hand, if it lights up, I might notice that I forgot to turn it off. It's fairly simple to make it. You just take your common voltage, in this case it's 4.5 volts. We know that's always half of the supply, and then we just use a Zener diode and a resistor to set our cutoff point. You should know that if you use a high value resistor here, which you probably won't, then the Zener voltage of the diode is not really valid. You have to experiment with that or look up the datasheet. You might want to use a higher value than you expect. If you set 3.3 volts, for example, to cut off at 6.6, you might notice that instead of regulating to 3.3 volts, it would be maybe 2 volts, because the drop is lower at lower current. In my case, I used a 4.3 volt Zener diode here. I built up the circuit here, and I guess it does look a bit messy. One thing I forgot to mention is the outputs here. You would like to AC couple, so just put a capacitor in series with the output. I chose 1 microfarad. I didn't mount the LED yet, but we have the circuit for the LED is the resistor and the Zener diode here. The common voltage I make with these 2 resistors, I botched a capacitor across it because I forgot to add this on the circuit board. This capacitor you see across the power pins here, you always want to have that. That was actually my intention, just to solder it across the chip, because that's where you get the shortest distance. This is a single layer circuit board, so if I didn't put it here, I would have to put it off to one side and run tracks into the power pins. It just reduces noise a bit to put it directly across the pins. Apart from that, it is as I drew the schematic. I added the XLR connectors, and that's the most expensive part of the circuit. I bought these from China around $0.8 each. These are a bit cheap. I think these were $0.8 and these were $1. They work okay, but it's not the best quality. It's not something you would like to use for professional gear. I just soldered up one channel so we can test it. By the way, I found that the op amp was a little bit unstable just going out into the output capacitance here to drive the output. So I added a 8.2 kilo ohm resistor to battery negative, just so that there's always a bit of current flowing. It seemed to remove the problem. So that will be from here to ground. To test it, I hooked it up to my power supply here, and I'm going to turn it on. We see that we get our power light. Actually, it's fairly bright. I could use a higher value resistor for that and save some power. Let me turn the input voltage down. It starts around 10 volts for a 9 volt battery, and it dropped out. So right around, oh, I was very lucky. My target of 6.6 volts. Actually, I did test this outside of the circuit. I tested it in a breadboard, and there I got 6.8. So probably just slight variation in the chip or the Zener diode. But remember, I'm using a 4.3 volt diode to get this. Because of the low current through it, the voltage will be way lower. I have experienced before that as you turn the input further down, it might turn on again. Let's check that. This op amp does operate all the way down to ground, so maybe we won't see it. No. My power supply only goes down to 1.2 volts, but it didn't turn on. And let's see, it turns on again at 6.6. And you can see the intensity of the diode changes with voltage. And that's because we're just using a resistor to limit the current. But it's okay, I mean, it's fine. But I guess the most important test is the sound, so let's try that. And if I speak into the microphone, hopefully we can see something. It looks like it's much better now. It looks like I can get it to clip at around half the amplitude, just speaking normal. Speaking very loud, it should probably be less. Until now, I actually have no idea how this sounds. So I switched over to using this microphone, and I put the level so that we just get the peak warning when I'm speaking the loud tones. This is the highest amplitude that we would comfortably record, and we can compare that to without the preamplifier and then boosting it digitally and see what the difference is. Yeah, but I'm excited to listen to this track and see what the performance is, if it's actually usable. Testing, 1, 2, testing. Testing, 1, 2, testing. So I just replayed the audio track, and I don't know if YouTube will pick it up because it does compress everything. But I noticed a slight whiny tone on the preamp that is not normally there. It's very, very low amplitude, but yeah, it's there. I did try to mess around with the circuit a bit, but I can't really get it to get away. I'm not sure if it's because it's exposed and not shielded. It is so low though that I will not really care about it. Just for completion, I put the component values on the schematic here. I will fix the mistake in the PCB and add the resistor to the output and the capacitor here that I forgot. And then I will upload it to my website. If you have any other ideas, you're welcome to post your comments in the comment section below the video. And I hope you will give the video a thumbs up if you liked it. Also, if you think that we should make a better version in the future that will accept all microphones as inputs, yeah, sure, feel free to suggest that. It would be a fun project, although I don't really have anything to use it for, but I guess I could replace this one with an even better one. This was really just something I wanted to hack together in one day and then use it, so I couldn't really wait for any components to arrive. Anyway, thank you for watching this video, and see you soon for the next one.